This story begins about 25 years ago when I initially learned these different methods or algorithms for solving calculations. We had addition, subtraction, and multiplication, and we learned them in that order. So then the fourth one was division. And well, I was a bit surprised because we then got to see a version where the starting point looks like this. It could have looked like this, or maybe like that. It didn't look the same as the other three. And already then, I started wondering, why can't division look like the other three? And but I didn't ask, because I figured I would probably get maybe some kind of slightly irritated response from the teacher, or, well, certainly not a good explanation. So I just kept it to myself. And now, years later, I started teaching students at a certain age that had not yet learned any kind of, algorithm for division. I remembered this thing that I came up with, and I decided to see if it was plausible. And to my surprise, it worked really well. So, I decided to write them in the exact same way as I would addition, subtraction, multiplication. I'm not going to explain in detail like everything in this video, because it's going to take way too long. So this is just a quick presentation of the method. It's a form of short division where you don't separately write down the subtraction when you calculate the partial remainders. So you just write them down, because I think that's actually a fairly easy thing to do in your head. And the most difficult thing is figuring out the actual division. So, it's just time consuming and maybe sometimes confusing to write all these subtractions like you do in long division. So this is a form of short division. We're going to start from the left. We're going to see how many times does 4 go into 5? One time, right? And there's a remainder, because 5 minus 4 is 1. So we write the remainder up here, the partial remainder. We take a look at the partial remainder and the next number, which is 0. So we have 10. How many times does 4 go into 10? It goes 2 times. And we have a partial remainder of 2. We can cross over the 10 because we've used it. 24. How many times does 4 go into 24? It goes 6 times. There's no partial remainder. It's 0. So in the next step, we only have the 8. 4 goes 2 times into 8. We are done. We have a remainder of 0, and we've used all the numbers. So that's your answer, 1,262. I'm going to show you some more examples, and they're going to get progressively more difficult. So bear with me. Here we have a divider that has 2 numbers, so that always makes it more difficult, because now you have to think in bigger numbers. So the first number is 3. Now 12 is bigger than 3, so it goes 0 times, and we still have 3 as the partial remainder. Next one is 35. So that goes 2 times. There's a partial remainder of 11 because 35 minus 24 is 11. And now you see we get a 3 number sequence, 1, 1, 2. And that goes 9 times. 12 goes 9 times in 112. There is a partial remainder of 4. And finally we have 48. And 4 times. No remainder. Done. Answer 294. Okay, so these were, you're thinking, well, there was no remainder. What do you do then? Yeah, so let's take the next example. 22 divided by 7. So some might recognize this immediately, but let's have a look. So we know that 21 divided by 7 is an even number, or you get a natural number as the answer. But 22 won't work, so we'll have a look. So 7 and 2, 7 is bigger than 2, so it goes 0 times into 2. We still have that 2 as a partial remainder. Then 22, well, 3 times. 3 times 7 is 21, so there's a remainder of 1. So at this point, we have used the numbers, but we still have that partial remainder. Now what we can do is we can add decimal. I use commas, some use dots, but same thing. So 22 is the same as 22.0. It doesn't change the value, so we can add as many zeros as we need. So now we have 10. And 7 goes once in 10. We get a partial remainder of 3. We can add more zeros. 7 into 30, 4 times. That's 28, so we get a partial remainder of 2. 20 goes 2 times, and so on. As you can see, we have 3.142, and yeah, that's actually pi, rounded up to 3 decimals. So 22 over 7 is a good approximation of pi. So let's have a look at an example where both the dividend and the divider have decimals. 9.8 divided by 2.8. So let's have a look. We have a total of 2 numbers in front of the decimal comma. We have the 9 in the first one and 2 in the second one, so a total of 2. That means that in the answer we will also have a combined number of, we'll have 2 numbers in front of the decimal. So I can already place it in the correct spot. You can also do it afterwards, but that's the way it works. So now we're gonna, when we're counting, we're gonna treat these numbers as if they didn't have decimals. So we're gonna look at them as 98 and 28 to make it a bit easier for ourselves. So 28 in 9, well, 0 times. We still have the 9 as a partial remainder. And then 28 into 98, that goes 3 times. That is 84. So we'll have a partial remainder of 14. And now we can add zeros. 140. Well, 28 happens to go exactly 5 times into 140. So we have no remainder left, and the answer is 3.5. So far so good. Now let's get wild and crazy. So we have a polynomial division, 3x to the power of 4 plus 9x to the power of 3 minus 5x squared minus 6x plus 2 divided by 3x squared minus 2. Wow. Okay, so how this works now with this method is we're going to look at 3x squared. What do I have to multiply it with to get 3x to the power of 4? Well, x squared. Right, because this multiplied by this equals that. Okay, we can now remove this completely. We have accounted for it. Next step, x squared, which we wrote down, we're going to multiply it with the minus 2 here in the divider. So that's minus 2x squared. That's going to change the value here. We're going to get a new partial remainder. So minus 5x squared minus 2x squared is minus 3x squared. Okay, moving on. So we have 3x squared. We're going to look, what do we have to multiply it with to get 9x to the power of 3? 3x. We can remove that. 3x times minus 2 is minus 6x. Okay, so it takes out this one completely. 3x squared times minus 1 equals this. So we can now remove it. We have 0 as the remainder from that. And minus 1 times minus 2 is 2, which takes out this final 2. And there is your answer. X squared plus 3x minus 1. Final example. Okay, we have 3x to the power 3 plus 5x squared y plus xy squared minus y to the power of 3 divided by x plus y. Whew. So, same principle. What do I have to multiply x with to get 3x to the power of 3? Well, 3x squared. 3x squared times y is 3x squared y, and that's going to affect this partial remainder. This is already 0. This is going to change. It's going to be reduced by 3x squared y, so we have 2x squared y left. Next one. So x times 2xy equals this. 2xy. That's going to remove that completely. And 2xy times y is 2xy squared. This minus 2xy squared is minus xy squared. So that's our new partial remainder. Finally, x times minus y squared equals this. So we're removing it, and minus y squared times y is minus y to the power of 3, and we're done. So this method is not found, to my surprise, in any books or anything like that, and especially some of these polynomial divisions, I was a bit surprised that all the methods really offered for solving, you know, such a division are way more complicated, I think, and so I think I might be onto something with this new version. I don't know, but if you have any criticism or questions, you can post them in the comment section, and I'll get back to you.